Hello, all. Here we are again, and we're going to be talking about section 1.2 and the things that we want to get out of this. You should be able to describe the basic properties of solids, liquids, and gases, distinguish between mass and weight. We often think of them as the same thing, but they're really not. Understand, be able to apply the law of conservation of matter, and classify matter as an element, a compound, a homogeneous mixture, or a heterogeneous mixture, and be able to define and give examples of atoms and molecules. So matter is anything that occupies space and has mass. And that means most things, but not things like thought, I suppose, although thought is mediated by matter, our brains, and so on. But matter is something that takes up space and has mass. And it can be a solid, it can be a liquid, it can be a gas. And it actually also can be plasma, but let's just stick for the moment with solid, liquid, and gas because those are the three biggies. A solid has a fixed shape and a volume. A liquid is going to conform to whatever container it's in, but it's going to have a horizontal surface. Then a gas is going to also conform to the container, but it's going to fill the whole container. And plasma is that fourth state of matter. Plasma is really an ionized gas. It has ions and a lot of ions, and we'll talk more in the course about what ions are. Plasma is found in the interiors of stars, and it actually is present in lightning. And in fact, any high temperature combustion is going to have enough ions to be considered plasma. And a plasma can shield an electric field. So it's kind of weird. Not very typical, but certainly present. And I suppose it's very typical in the universe since it's what the centers of stars are composed of. Acetylene torch, which would be a torch that's burning a compound called acetylene, which burns at a very high temperature, could be considered a plasma torch. So it's a practical example of plasma. Mass is the amount of matter in an object, and weight is the force that gravity exerts on that mass. And an interesting little point here that our textbook makes is that something would have the same mass no matter where it was, but if it was on the Earth, it would weigh more than the moon than it would on the moon because the Earth has more gravity, stronger pull, giving it more weight. Law of conservation of matter is something that shows that says that there's no change in the total quantity of matter present when some sort of a conversion occurs. A chemical change of some sort, typically, is not going to change the amount of matter in a system. And it's true for both chemical and physical changes. It's somewhat hard to observe sometimes in the laboratory because usually we lose track of a little bit of matter in the course of an experiment. We spill something or something will escape into the air, etc. But if you were able to do it carefully under controlled conditions, you would see that there's no loss in the total amount of mass kind of no matter what happens, that mass is still going to be around in one form or another. And there's some examples in your textbook. One of them being the discharge of a battery. Batteries such as the lead acid battery that we have in our cars and other places produces energy in the course of the chemical reaction that takes place in the battery, and lead and lead oxide that are surrounded by sulfuric acid react, and as they do, they cause a flow of electricity. When the battery is completely discharged and it can't produce any more electricity, we've still got the same amount of mass, but it's changed in form. It's no longer lead and lead oxide. It's now lead sulfate and water. And don't worry for now about these formulas and what they mean, and I'm just sort of rattling them off. You'll learn as we go into this course how to say, okay, yeah, that's lead oxide, etc. Don't worry about that for now. We'll get to that. An element is a type of a pure substance that cannot be broken down. It's as far as you can go in terms of breaking something down into its smaller and smaller and smaller elements, as it were, the smaller and smaller and smaller particles, pieces of something. You get down to something that can't be broken down into anything simpler through a chemical change, and that is an element. That which cannot be broken down further by a chemical change. And elements are displayed in what's called the periodic table. Elements cannot be broken down. Compounds can be broken down into simpler substances. An example would be a reaction of mercury oxide. It's heated. It looks like a powder. You heat it up, and lo and behold, you've got metallic mercury there and a gas which has disappeared. Example of a chemical change. A mixture is two or more types of matter that can be separated by a physical change. So when water evaporates, it's changing from a liquid to a gas, but it's still water. Hasn't changed chemically. There are a couple types of mixtures: homogeneous, which are uniform throughout, and heterogeneous, which aren't. Homogeneous mixture is a solution. Heterogeneous is not. And a couple examples: a heterogeneous mixture that we're probably pretty familiar with is oil and water, and you could think of it as salad, oil, and vinegar, which is mostly water, but it's got acetic acid in it. But water and oil don't really mix, and you can shake them up and you'll see bubbles of oil surrounded by water, and if they sit for a while, the oil and the water will separate. So that would be heterogeneous mixture. And a jar of Gatorade or the like is uniform throughout. There's nothing about it that is different from any other part of it. So it's a homogeneous mixture. It's a little decision tree here. Walk yourselves through that. Does it have constant properties in composition? Yes or no, and so on. And that will sort of tell us whether something is a heterogeneous mixture or a compound or an element, etc. Atom is the smallest particle of an element that has the properties of that element. And the concept of an atom has been around a long time, but it wasn't until the 19th century, the 1800s, that John Dalton actually made some headway in understanding that matter is composed of atoms. And a molecule, these are some of the language of chemistry, the terms. A molecule is two or more atoms that are connected. And there's various ways that happens. We'll talk more about that. But the way that the atoms are connected are known as bonds, chemical bonds. And so a molecule is different from an atom. It's composed of atoms. Here's an interesting picture done with what's called a scanning tunneling microscope that reveals the structure of a gold nugget at the microscopic level, submicroscopic. Really, these little spheres are gold atoms. And as we go to more and more intense levels of magnification, the molecular structure can become apparent, although it's pretty hard to really see a molecule in the same sense that we see a ball of cotton. But these images reveal what it looks like under magnification and modeled magnification when we get down to the molecular structure. Atoms can combine to form compounds. Here's some examples. Compounds can be separated into their elements through various means. Here's the electrolysis of water. And that's, I think, enough for this time. We'll get on with section 1.3 in the next little video. So over and out for now.